a path towards smart vision sensors and solar energy harvesters. And of course, 3D and energy harvesters are topics that are dear to our own hearts. We've been involved in many of these topics ourselves in our own research here at the Masdar Institute. Just a short introduction for Dr. Safir. He received his BS in physics in 1996 from University of Satif, in Algeria.
That's right.
And then went to get an MS from the University of Malaya in Kuala Lumpur, Malaysia. And then on for a PhD in University of Waterloo, Ontario, Canada, where he graduated with his doctorate in 2005. In 2006, he joined McMaster University in the Communications Research Laboratory. And of course, a pretty consistent career in R&D, especially in sensor design, in imaging design, in CMOS imagers, and in all kinds of instrumentations related to imaging. His most recent affiliation is his affiliation as a research fellow at KAUST, where he developed the smart nanophotonic devices for imaging and solar energy harvesting, which I assume is the very topic that you are going to talk about.
Exactly,
Dr. Faisal. So now he's faculty with our colleagues in the EE department, United Arab Emirates University. He still has some affiliations with Canada, University of Guelph in Ontario, Canada, and he's been also still visiting with University of Waterloo and University of Canada. He had few collaborations, international ones, and currently pursuing an MBA. So it seems like it feels like somebody who's on his way to start a company, with the ideas that he's been developing. And he just wants to, to get the business side right.
Exactly, to hire people.
Okay. So, which is really, by the way, it's a very good move.
Thank you.
They really can't play games on you anymore. Once all these business people. Right?
That's it.
So he knows
you know the plans. That's it. It's over.
All right. So without further ado, I'd like to welcome Dr. Faisal to the podium to share his presentation with us.
Thank you very much, Dr. Ibrahim. It's really a pleasure to be in this great institute, Masdar Institute. And thank you so much for your invitation, Dr. Ibrahim. It took a while to get established. 1 year, exactly. It took 1 year for us to prepare this, for many extremely busy people. So what can we do? We just survived that. So without further ado, thanks for the nice introduction. It's not the life take us in different venues. So before I talk, I'd like to present just. I'm not sure if I can do that here. Oh, I'm not sure. So let's say.
Sometimes the pointer doesn't work with this projector. You can't see the point. So sometimes you have to point.
Actually, I did it before, so I think I
have to use your cursor something.
Exactly. Yeah. So just a very short, just 1 minute introduction of my channel. What I will talk about this.
It's a wonderful day.
My homework.
My name is Dr. Faisal Safi. I am presenting in the following videos some talks and seminars
and that
I gave in Canada, particularly Polytechnique of Montreal, University of Waterloo, Intelligence.
That's my basically the summer.
Intelligence Society of IEEE, and other universities like Ramsey University, Windsor University, and that's it, 4 of them. I present my research. Also, you will find in the following, not only that, those also that I haven't mentioned because they haven't scheduled yet. I also present a seminar I gave in St. Petersburg, Russia, about my research. I hope you will enjoy it and welcome all your feedback. Thank you and have a wonderful day. Bye-bye.
So that was an extensive, visit I had. Sorry about that. Oops. YouTube is crazy these days. Okay. It was during a visit I had this year at the University of Waterloo, where I presented many talks regarding my approach in developing CMOS image sensors. And the approach I took for that, it's not really something I have chosen. It's something that I have admired since a long time ago, but I never had the chance to think about it until I was hit in my master's by working on artificial intelligence, basically neural networks. That's where really I started to study the intelligence. I thought that intelligence is something that we use and that's it. But apparently it's actually something we can harvest as well. So before we go deep, let's define intelligence. Intelligence was really something that intrigued the mankind since ever. Since the Greeks, since this guy, Socrates, he defines the intelligence. He said, very interesting quote, he said that I know I am intelligent. So why? Because I know that I know nothing. These guys, Socrates, define in this statement what we call the self-awareness. And the self-awareness is the next bridge to make artificial intelligence dominant in the business. And that's what really Google and the big AI players are working on. But nonetheless, it's just one definition. Einstein later on came with another definition. He said, listen, intelligence is not about knowledge, actually. Intelligence is about imagination. So different people, they define intelligence different way. It depends where they are coming from and stuff like that, and what they, how they look at it. So different angles. So this angle of Einstein is basically shows the creativity, because imagination is related to creativity. Great. To make things even spicier, the psychologists nowadays, they define intelligence in different spices. People they call analytic intelligence, they define also linguistic intelligence, emotional intelligence, etc., etc., social intelligence, you name it. Why? Because they find this intelligence widespread. So it's a multidimensional aspect. So what is really intelligence? Nobody knows exactly what it is. So the bottom line is that there is no consensus about intelligence. Good. So what? So let's look at the intelligence through our perspective, through engineering. We don't need to know what's the mass, for example. We don't need to know what's the electron. We don't need to know things that are physical, but yet we use them every day. After 30 years of work on photonics or photons, Einstein, who got the Nobel Prize not for his relativity theory, is actually for the photoelectric effect, the bottom effect that is behind all these technologies in PVs and imaging. He said after 30 years of work, we don't know what's photon. He got Nobel Prize for that. It's because we don't know the reality of the material world. We know the effects, but we don't know what's the exact reality of them. So let's harvest this intelligence. So first and foremost, let's see where we are using the intelligence. So we say that, okay, fine, the intelligence is a faculty, a talent, an aptitude, or malaka in Arabic, that inherently found in humans and animals as well. Okay? And this basically is the cause or responsible about solving problems or complex problems in terms of optimization, basically. Okay? So in here, basically we are using the intelligence through the heuristic processing. Means that we don't have a methodology A, B, C, D to solve a problem in here. We use these techniques, especially in artificial neural networks, to apply or use intelligence, but we don't know exactly how they are working. That's why it's a topic of research and still we are using it. And yet there is applications for it in your phone, in the internet. I mean, there's a huge application behind artificial neural network. The second aspect of intelligence that we are using nowadays is actually in your phones. It's basically for this aspect of functionality integration. If my phone can play music, make phone calls, control my car, you name it, you integrate the functionalities, and that's the intelligence. Now, why you call it intelligence? Is because the brain itself is doing that. So the brain is responsible for hearing, sensing everything, processing. Not only that, actuating, controls eyes, legs, etc. So he takes many things, process many things, and do many things as well. So the brain has what we call functionality integration. Very, very important aspect of intelligence that in engineering we do. In your mobiles and etc. Good. So this is the second application of intelligence. Also, intelligence is thought as related as to how the world was made, or basically how it's made, basically, or the stratagram. How is really the world is working? It's really something that intrigues people, and we can find here a lot of things that we can learn from the universe about the intelligence, how it's embedded in the universe. Okay. The last but not the least is also intelligence is used as extracting information. That's another aspect of that. And for that, it's very easy. The CIA, the I stands for intelligence. So intelligence is to extract also the information. Okay, so it's related of the intelligence to intelligence. So extracting information as a security application is part of the intelligence, and of course it makes sense by all means. All right. Okay, good. Two statements, they have inspired me to look at the aspect of intelligence. And you can see later on why this is related to CMOS and CMOS imaging. Just bear with me a little bit. So, two statements, one by this guy, a Greek guy, Aristotle. He said that nature does nothing uselessly. Everything is with purpose in this universe. I'm talking absolutely materialistic way. The other side, the metaphysical world, that's a different story. We're talking only about the physical world, meaning photons, what materials, etc., how the system works. So, in that aspect, nature does nothing uselessly, everything for a purpose. We'll come to this later on as well. And the second, which is the blowing statement by this guy, Kepler, in the book of Carl Sagan. He said that the diversity of the phenomena of nature is so great, and the treasures hidden in the heavens so rich, precisely in order that the human mind shall never be lacking in fresh nourishment. Okay, if you feel like you are tired and you don't have ideas, go to the beach or the mountains and you will be impressed. All right? Good. All right, good. Let's move on from here. Where we go? Let's see what we know, and let's see what we need. What we know is that the intelligence or intelligent design of biological systems are proven over a long time, right? So the biological systems, and that's where really I'm trying to learn the intelligence or extract it, has seen everything, okay? So if you want to say it has a full of experience, billions of years, so it has the solution of what we need. What we need is that in engineering, we always face a multifaceted problem. It's not a single problem. We face a problem that has many dimensions. As you know, for example, in electrical engineering, when you shoot for speed, you pay something in the power, for example. See? So it's a multifaceted problem. Not only that, and then comes the cost. And so it's a multifaceted problem that in the sense of, it's an optimization. An optimization, there is no better than intelligence. Okay? Good. So let's learn from here the intelligence and apply it in here. Learn from here, apply it in here. Boom. And that's what we call biomimicry. Or biological intelligence mimicry if you want. But that's fine. The aspect is that, or the point is that we learn from these guys the intelligence, apply it for these guys to make business, to make money. And that's where I got into the area of artificially intelligent CMOS imaging, or AI square. AI square, by the way, it's a formula of power, right? Where A is R, and I is the current. Current square R, yes, it's the power, right? So, but the power in here, we are talking about intelligence power, which is something that is different from the regular power. Good. This is just, just to give you a quick snap of what's a CMOS image sensor or an imaging system. It takes the information from the light coming from the scene, focus it through optics, acquire it through microlenses, color filters, and converters, or photodiodes if you want. Digitize them, make the image, process the color, enhance it, boom, you send it. So these are it's like the system in a quick snapshot. All right. And this is basically the core of an image sensor, a CMOS image sensor or a CCD image sensor. Is basically the converting or transducing side plus the digitizing side, and the rest can be also embedded in a chip to make an SoC or system on chip. This is just just a snapshot of a microelectrograph of a chip of an image sensor, where we have the sensing area, the processing area, controlling circuits. Nothing really fancy about that. Now, good. Before we go even deeper and deeper, the first thing that when I approach this idea of embedding the intelligence to a CMOS image sensor is that I started just taking this the aspect of scanning or sampling. Okay, so I said that scanning or sampling is not necessarily has to be adaptable to the image display. The image display, we know it's working as using a scan. So I said, okay, let's change the sampling or scanning for an image sensor from raster to something else. And that something else is dictated by our need, not by the display need. Okay, that's good. And on the other side, I said, okay, fine. The biology does not treat the image at the same weight, meaning the optical axis is basically where my interest is. So if I read, I don't read like that. I read facing the letters. Why? Because the system gives me the resources enough to resolve very well the information in front of me. And that's where the biology is doing. So it's not treating the image at the same weight. So only the areas of interest, or what they call ROIs, is not return on investment, it's actually region of interest. They give them the highest resources. But that's fine. Good. So, how we extract intelligence? Well, we learn from biology. How we learn from biology? We look at the biology and see. Good. So this is the plan. So what we know? What we know in engineering, that CMOS image sensors, like any electronic system, is limited by resources. Yes, to acquire high resolution or definition imaging. We'll see that in a second. So resources also include the memory, include processing power, include time, etc., etc. So that these are what we call constraints. Good, they're good. What we know more is that not all the areas of the image that we are acquiring need to be treated at the same degree of importance. Okay, DOI. Okay, good. So we need to give or allocate resources only to a region of interest. Good. So only then, so that's the candle, only the region of interest are sampled at the highest resolution. The rest, they can take less resources. Okay, good. Looking at the biology, this is what we know since the 19th century. Okay. So the guy here, Ramon Cajal, is the guy who studied the fovea. The fovea is basically, if you look at the eye, is actually this part is actually part of the retina, which is the sensing side of the eye. Okay, and the fovea is just the center part, which is this one, which happens to be at the optical axis of the eye. So basically, what you see, the center part of your vision is actually the fovea. Good. So he looked at that and he distinguished two types of photocells, rods and cones. The rods and cones are two different photosensors. The cones, they are distributed close to the optical axis or close to the fovea. They are highest density, and their density decreases out of the fovea. However, these are the cones. The rods, however, they are higher at the periphery of the fovea, it means outside the fovea, region of interest, or optical axis, and they are actually higher outside. Good. What we know also is that the cones, they are responsible about color filtering. The color filtering happens with these guys, with the cones. That's number one. Number two, they are responsible about what we call the photopic vision, means the daylight vision. They are very good at daylight vision. The rods on the other side, they are color blinded, means they cannot look at the colors, and that's why they are good at night. Who cares about colors at night? No one. And that's exactly what they are doing. Good. Okay, fine. So this is what we know. One more thing, of course, in the daylight, the light can go up and low. That means the columns here in the center, they have what we call high dynamic range. It means the ability to see bright and low light. Good. Thank you very much, Mr. Kajal. I really appreciated that. And then from there, I took on the implementation of the intelligence. 3 levels: the system level approach, time domain; the circuit level approach, spatial domain; and the device level. We'll talk about that later on. Okay. Very quickly, I'll go through that, and I'm not really expecting you to be expert in here, but I want to emphasize on some really interesting aspects. In the system domain, basically, we tried to what we call create synthetic dynamic range. It means a dynamic range that is not dependent on the device, photodiode in this case, but is dependent on the system, how it synthesizes the image. Because you can enhance the dynamic range using the system, and you can find that also in most of the phones. So basically, it takes multiple images and then fuse them and get a good one, so that the bright are not overexposing and the dark, they are a bit enhanced. And that's the nice thing to do. In here, to implement this, the cameras that we have, or most of the softwares as well, what they do, they take the whole frame and take multiple frames and then fuse them. Take the frame with short integration time, means you look at the dark spots, and you take long exposure time to look at the, short integration time to get the bright spots, and short integration time to get the bright spots. But here in this approach, we said no, that's not what we're going to do. We are going to implement it at the scanning level. So in the classical camera, in the classical CMOS image sensor, so the pixels where we have the photodiodes that we sample the image, they are actually rows by rows, and we read them one by one, and then we come back to the first row and we do what we call the rolling scanning or the raster scanning. Okay? In the suggested modified scanning scheme, actually we do it not in one-dimensional sampling like the raster scan, we do it in the ring scanning. So in here, so basically we sample ring by ring and then we go up, okay, or down, okay? So the scan is like an iris, like the eye is opening, closing. Good. So of course, to do that, you have, these are the column buses. Of course, when you sample one row, you dump it into sample and hold circuitry. Here, of course, they have to be oblique, means that the column bus or the output buses, they have to be oblique in this direction, and the sample and hold will be in the periphery like shown in this picture. So this is the, and that's why we call it pyramidal actually. I love the pyramids, really, they are nice structures. So if you look at the pyramid from top, what you see like a concentric squares, okay? These are the concentric squares, and that's how I call this a pyramidal imager. It's basically looking at the pyramid from the top, okay? And what you see here in the periphery of this picture of the chip is basically the sample and hold circuitry, basically capacitors, and you have coders there, or decoders to be able to get the output of the columns out. Good. So this is the first chip, okay? This is at the hardware level, but you need to control this circuit. For the controlling, we also said that, okay, we scanning, we change how we sample the camera. Also, we need to change how actually we take these samples. So in the raster scan, basically go row by row, and then you go back. Why you do that? Because you need every single row to have the same integration time. Why? To make sense, okay? Because if they have different integration time basically the opening to integrate the light. If they are different, so the image will not be consistent, okay? Not consistent means that it's misleading us. And that's why the raster scan is like that. Okay, great. Now, I said, okay, sure, why not? In the suggested architecture, we said, no, we are not going to do that. We are going to change the game in the following. We go ring by ring, so this is basically what you see here, is basically a cluster. Let me show you that. Is basically this cluster. This cluster here, unfortunately, this one doesn't work there. So is this cluster, this triangle. And you have basically 1 to 8 clusters in here, okay? All of them, they look like a triangle. So basically what we are seeing there is just one cluster like that. So in the suggested architecture, what we do, we basically said, let's go from the inner ring and then open, and then when we reach the end, we come back. Meaning that the the integration time of the rings, they will be different. In what sense? If you take the axis for each ring, in this particular image sensor, I used 64 by 64 pixels, very small, so don't expect too much in here. It's a university, it's not an industry. So we have basically 32 rings, okay? 32 rings. Now, if we look at the integration time, for the blue one, what you see here is actually the outward scanning. When you go out, and then you bounce at the edge, then you go in. Out and in. When you go out and in, basically, the time that you visit the row, you have to subtract it from the previous scan to calculate the integration time, and therefore, each ring will have two integration times. One for outward scanning, means going out like that, scan, and one for the inward scanning, going into the center. So each ring will have two integration times for a reason. The reason is that if I combine now the pictures, or the picture for the outward scan and the inward scan, not only I will find the same integration time for all, that means, like for example, the resolution and the display, they are not compatible, otherwise the picture would be looking better. Like for example, the inward scan here is like, it has a short integration time at boundary, and then the integration time is higher at the center. So that's why it's brighter at the center. The inward scan, which is, so this is the inward, this is the outward. The outward scan, however, it's brighter at the periphery and dark at the center. When you combine them, you get just a uniform picture. But that's not the end of the story, okay? So here, what I want to show here is that the total integration time of the fused image, this plus this, is actually uniform. But there's a more aspect to that, is basically when you do combine two pictures with different integration times, the dynamic range get enhanced through a formula that is well known in the literature there. And the dynamic range means ability of the imager to see bright and low get increased at the inner ring and decrease until it reaches a point where it doesn't get enhanced, and then it goes upward. And why is that? It's just because at this point, the inward and outward scan, they are the same. So if you fuse them, there's nothing that you're gonna gain actually. So the gaining, as you can see, what we meant by dynamic range enhancement is that because the integration time is low in here and high in here, means that this ring will be able to see bright spots very well and badly the dark spots here, and so on and so forth. And that's why the integration time is like this. In 3D view, it's like that. But we can do more. We can change the integration time entities, basically a T-sample of the pixel and the row, and we can make that boundary at the periphery in here, okay? And now the dynamic range is actually foveal. Foveal in the sense that the dynamic range at the center is high and outside is low. Wow, we are reaching the goal in here. And the goal in here is that when the dynamic range is high, the A to D converter will need more bits, okay, to convert that information. Means I have too much information here to sample. However, when the dynamic range is low, I don't need too much of bits to sample. So in this case, I'm allocating more resources in here in the optical axis, or fovea if you want, and less hardware resources for the peripheral rings. Good. So we basically achieved something that is similar to the biology. So it looks like the cones distribution, because the cones, which have higher dynamic range, they are higher at the optical axis, means the center of the vision system, and they are low in density at the outside that axis. Very good. Here just some experimental results. So I was in the office in here taking. Unfortunately, they are not looking very well here. But if you take two different scans, inward and outward, and fuse them, you get a picture that here, the bright spot here, it can be visible. For the rolling scan, it's completely blown away. You cannot see the details. Unfortunately, the resolution is low and the display is not good. Otherwise, you can see this picture much better. But relatively, because they are suffering from the same problems, this is much clearer than that one. Okay. The same thing for this, but here I'd like to, I was trying to show the periphery, but that's fine. But here, just want to show that yes, experimentally, it does make sense like theory expected. Good. Here, just another result of having this 2D sampling of the rings. Basically, the speed of the camera will increase basically because we are dividing the camera or the image sensor into 8 pieces. And that's was not the aim in any ways. The other outcomes of this architecture is that it minimizes the blur. So if you take a regular camera and the pyramidal camera, you can see that the motion blur here is more visible than the motion blur in the pyramidal sensor, basically because the 2D dimensional sampling. Or in other words, that the biology is something, the biological systems, biological imaging system does not take the information like serially like we do in the raster scan. This is another outcome of the camera. It's not that of a big deal, but what I wanted to show in here is basically the human visual system or biological system is actually less sensitive to the oblique frequencies, okay, but it has higher sensitivity into the cardinals. Means that if you take the Fourier transform, the sensitivity is actually higher in the vertical and horizontal, is less in the oblique. And this is really good news for our system because simply our noise in the pyramidal image sensor, which is this noise, is actually mainly in the oblique axis. And I published a paper in this, and it was a nice one. The second implementation, which is the circuit level. So we said in this approach that, fine, let's keep the scanning or the sampling the same like the standard CMOS. And what we're going to change, we're going to change the pixel. And we are going to change it in the sense that only the region of interest, we take them at the highest resolution. Those who are not interested, what we are not interested, we basically average them. We take the average of a block and then we move on. This is too much of a talk, and here we define multi-resolution image sensor. Here's the idea. So this is a part of the CMOS image sensor here inside the matrix. So basically in the areas that we are not interested, like a periphery in here, if we are not interested, we implement what we call charge sharing circuitry, where we basically brush these rows like this horizontally, and then we brush them vertically, and then we read only 1 pixel out of that area because I'm not interested. I just need the average. And I'm not talking about myself, it's actually the application that speaks like that. So for that, we developed this circuitry. We have basically these transistors. They are responsible about making the charge sharing between a local capacitor and the neighboring pixels in the columns and in the rows. And this is cadence simulation. These are the applications that we can use this image sensor. It's basically we can have central phobia around the mustache of Albert Einstein, or we can have a random phobia. We can have it through the tie and the nose. What I'm saying in here is that the phobia does not have necessarily to be in the center. We can have multiple phobia. And this is also part of biology because some hawks, they don't have one phobia. They have actually multiple phobia. And that's really amazing. Well, because they adapt to their environment to chase for their food and stuff like that, so they need really a more complicated vision system. And here in these two pictures, what we wanted to show is that sometimes the averaging does not kill the information. It kills the information that is redundant. So for areas that are not in the same direction of the kernel, we can do the averaging without losing of information, and we will basically gain the data volume will be actually more optimized to the data information. The last approach, which is the device approach, we'll talk about it at the end. But before that, we look at the big players, or basically the CMOS, the standard CMOS, versus the CMOS imaging, which is the core of our talk. So these are the main players. The main players in the business of CMOS imaging are basically Sony, then Samsung, then OmniVision. They take most of the share of market share of CMOS image sensors. And the forecast is about 13 billion by this year in the market of CMOS image sensors. And what we learn from here is that it's not only from here, it's a bit crowded, but to see that the major player here is Sony, and for a reason why Sony is the biggest player in here. And actually, it's actually the manufacturer of the image sensor of iPhones, especially 6S and forward. And you'll see why in a second. Now I want to really draw your attention to the fact that CMOS, standard CMOS, and CMOS imaging, they share something in their path and goal. Maybe because they share the same foundry, or maybe they share the same interest. CMOS imaging and standard CMOS, they are targeting high integration for a reason. For the CMOS imaging, of course, the higher megapixels, the better is the resolution, and you want also to get better quality. That's the target. So all the CMOS imaging players, okay, they try to have more pixels in image sensors than anybody else, and they also want that at a good quality. These two things, they are actually fighting each other. And you will see that in the next slide. The standard CMOS, which is the IC business or industry, they want that to integrate more transistors to basically integrate more functionality in here. Okay? They want to integrate more functionality and that the processor can do more stuff in a very small area, of course, with the lowest power and budget as well. Okay? So both of them, they want high integration for different aspects. This one for better quality of an image, and the standard CMOS for more functionality. Good. That's why the CMOS actually, what's really interesting, that CMOS, standard CMOS technology, started to move on from the plannar CMOS to the FinFET. Okay? The plannar CMOS is basically two-dimensional transistor. Okay? The FinFET, however, now is getting 3D. Okay? So it started by the late 1990s by these two papers. Okay? And then later on, what happens? The industry catch up. The SRC and AMD fund project, they start to catch up on these, and they try to make basically the new device more compatible with the process, with the standard process or conventional process of plannar CMOS. It's not easy. Going from 2D to 3D is not an easy job. So they started early 2000 to invest in this business, and they come up, and nowadays FinFET is the dominant transistor of all CMOS. Okay? And for a reason, why they moved from 2D to 3D? We'll see that in a second. DARPA, which is the main supporter of microelectronics and research in the US, also they jumped in and they started working on standardizing this technology. A very good resource is this Su J. King Liu, a very good really review in here from the UC Berkeley. He talks about the history of this, and I found it really fascinating. In any case, now the industry has adopted the 3D FinFET, the 3D MOSFET. Now, for the CMOS imaging, however, they also went from 2D to 3D, but in totally different approach. The initial technology was called the front-side illumination. In the front-side illumination, sorry about the quality of the display, I don't know, I have nothing to do about that, but I'll try to explain in here. So the light will come from the top, and the first thing it hits in the image sensor or CMOS image sensor are the micro lenses, the blue ones that you can see here. And the role basically is to collect more light. It's not to focus the image, it's to get more light. Why? Because they want to boost the signal in here. And then from there, the light goes through the metallization, like you can see in here. This is just an oxide in here, and through it, there's interconnects, okay? And then the photodiode is in the bottom. So this causes a lot of loss, as you can see. Some of the light will get reflected by these power lines, interconnect line, etc. Very little light will come there. Meaning that if you shrink the pixel, if you want to have more integration, very little light will come there. And that's why the industry suffered with this technology initially. Then Sony came up. Sony came up by 2010, even earlier than that, and said, okay, let's now bring this photodiode close to the light. And how to do that? Okay, fine. I take the micro lens and the photo and the color filters and put them at the bottom. Boom! And then now the photodiode now becomes in the top, and the interconnects in the bottom. And that's why we call it backside elimination, because now it's not eliminated on the front side, which where the interconnects are, or were initially. Now they are in the back. So now when the light comes, it sees directly the photodiode. Not only that, they needed to do something even more interesting. They needed to fully deplete this area to have a very efficient collection of photocarriers. Okay? Without that, there is also a big problem. So this technique also get now more fancier by putting another chip and bond it in the bottom, okay, to make more processing if you want. So here you collect the light, you do sampling, blah 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 blah, and here you make the fancy functionalities, whatever you want, face detection, you name it. It's done in here, and the technology of bonding or chip bonding became really something hot in the business, and we are talking now 3D stack BSI. So as you can see, the 3D integration or the 3D evolution of CMOS imaging came at the manufacturing, but here not at the device level, at the chip level. Okay, so that's a different thing. So standard CMOS did the 3D integration or 3D evolution at the device level, not at the chip level. The business of CMOS imaging, they did it what? They did it at the system level, at the chip level. These are the main changes or main differences between the evolution of standard CMOS and CMOS imaging. Good. That's interesting. Here, I take you to my approach to this. And before that, I have to drag your attention that this technology is cheaper than this, and this is cheaper than that. Why? Because going from this technology to that technology, this one takes 2 wafers for every single wafer for this, to make the backside elimination. Now this one will take what? Will take 3. Because not only you need 2 here, but you need another one here. Without counting the bonding issues and stuff. And trust me, I worked in the US in a startup company. It's not easy. It's a very complicated business. So the cost actually increases this way. But standard CMOS, of course, thanks to the research, they are not really paying too much for the FinFET. Of course, there's an added cost, but it's not that crazy. So I want to tell you that because I'm going to talk about that next. So here, the origin of my last implementation of smart imaging, which is basically the device level implementation of smart imaging. Good. So this is a sketch of a pixel, a standard CMOS image sensor pixel. So the micro lens in there, underneath there's color filter, of course, because we need to filter the colors to get a good picture. Underneath of that, there's transistors, and there's a place for detecting the light. So the light gets detected where? At the photodiode, that need to be reverse biased. Good. And then what we do, so this is the classical CMOS. Now, when you move on, when you try basically to shrink the pixel size, why you want to do that? You want to do that because you want to increase the resolution, meaning that the market tells you, listen, your competitor have a, and by the way, now Sony actually is implementing or designing 40-something plus megapixel cameras. So they are competing with high resolution. So the market dictates the resolution. Customers are looking for higher megapixels, for higher resolution. So the designers, who are you, of course, and me, they say, okay, fine, we want to do that, we have to shrink the pixel, because we have to keep the same size. Okay, good, but if we do that, we compromise the quality of the image. Why? Oh, it's very simple. Let's go there. Because if you make this smaller and smaller, what do you face in the front side elimination, as I've told you? If you do that, you basically minimize the amount of light coming here. I'm already losing in here. So if I make it smaller, almost nothing will come there. Not only that, the transistors also, they contribute with noise. So at the end of the day, what you get? 0. A black. And that's why if you want to test the camera, test it in the night, where you don't have much of light. That's where you say that your camera is good or not. And that's why I bought my car. I test the rear camera in the night. Why I like it, boom, take it. So that's where really the pain is. Okay, great. So if we move from there, okay, that's the industry. Okay, let's see. Oops. Some technical issues there. Okay, let's see. All right. Good. So the idea is that, fine, I will try to push a crowbar here, and I will try to make this separate, or make them decouple them technically, making the resolution count independent of pixel size. Meaning, I give you the bottom line of the pixel size. You cannot compete with that, and I can make that as large as you want based on your frame. Good. And why I want to do that? Because the biology did it. You see that in the, oops, I don't know why it's, maybe I have to switch on and off. It's not. Okay, that's fine, I go to the laptop. We're almost at the end, so it's not a big deal. Good, because biology did it. So, in biology, remember, if you take, again, sorry about the retina, the photocells in the retina, they are not plannar. They are actually elongated structures. They are elongated structures. This is the real micrograph picture of the retina. Here is the sketch. So basically, they are elongated structures, meaning the light, when it comes, actually it comes from the bottom here, it passes through the ganglions, which are the neurons, and then along that path, the photocells will try to sense the light. They are not plannar, because the biology is not stupid. Why? Because they take the smallest footprint available, okay? And then they elongate on this direction to maximize their harvesting of the light. You see? So they are maximizing the light conversion, or to in this case chemical signal, or electrochemical signal, maximizing that signal over the footprint. Footprint is very small here. That's why you have the highest resolution in your eyes than any other camera. And in that case, we said, okay, fine. In that case, let's make now the photodiode that we have elongated instead of plannar. And that's where the 3D evolution, but the 3D evolution of CMOS imagers here at the device level. Good. Okay, what's next? The next thing is that we need to make calculations. That's what the engineers do. In a paper I presented in ISCAS in Rio de Janeiro, Brazil, in 2011, I think, or 10. I think 11, yeah. I come up with a formula here, semi-empirical formula, in which I have proven it was a surprise that the sensitivity is proportional to the height. And that's really something very important, meaning that if I make this longer, the sensitivity, it means the ability to convert the light into photoelectron carriers, will increase. That ability increases. That's very interesting. And what is really most striking here is not my formula, is that some bullfrogs and some fishes, they do exactly that. That means if they are in the night, not only their eyes get larger and larger, their photocells elongate when they are in the low light conditions at night. Meaning they are boosting their sensitivity in the night by elongating themselves. Means H increases. And when there is too much light in the daylight, they just contract because they have enough photons to harvest, and there's no need to increase the sensitivity. That means the biological visions, they have already proven this. So right now, that's exactly what I'm doing in my research. I'm working on developing this in TCAD2s, and I have some proofs of that, and some work has been published, and some other work is coming. But that's exactly where the intelligence is doing in here. We are biomimicking the intelligence of the photocells of the biology. This is some work I've done at the University of Alberta, okay, in the summer of 2011, where we have developed, using a lift-off technique, the photo pillars. And still we are working on this with the University of Waterloo at the Quantum Nano Center, okay? So next is basically the lab work. So basically, this is just the test structures we are developing. Okay, I have already the mask for this and all these things. So basically, we start with the mask for the pillars, and then I have to now go quickly here because I think the time is up. So so the first thing is we develop the mask for the pillars. But before that, we have to dope the front and back of the wafer or the dice. Okay, we have to start at the wafer level, and then after that we deposit the mask, and then we actuate. We dope at the beginning the front side, and then we actuate that part. Okay, and then we try to basically implement the pillars and then characterize them. Some applications that we were targeting and still targeting with this is the first thing that we are looking at is to have a system that is a camera system, a CMOS imaging system that is basically batteryless, that it doesn't need any battery, meaning that depositing on the top or building on the top a harvesting system here using the same photodiodes, and that's why the imaging can have the solar energy harvesting, and then supplying the energy we are taking from the top, okay, supplying the microelectronic system underneath, or CMOS image system underneath, and basically the camera not only will take the image information through the photodiode, it also takes from the light, from the surrounding light, the power to harvest it, and that's where we come up with this this coined word, sensor harvesting, sensing and harvesting. And the applications we want to do with this kind of concepts, basically the wireless endoscopic capsule, these are cameras that you can swallow, the camera phones, and the automotive industry, okay? To name few. One more thing before I go beyond that, is, and I will talk about that in maybe in the next slides, is that the plannar CMOS imaging was actually suggested in the early 1990s at JPL, Jet Propulsion Lab in NASA, by modifying the CMOS fabrication, okay? And that's where this CMOS imaging starts to be really interesting. And we need therefore to modify it a bit to make vertical CMOS imaging like the same way that the FinFET has been done. The biological smart vision was inspiring in all these designs, and we learned a lot from this, to basically tackle the limits of the current electronic imaging. And that's where I want to take your attention in here, is that the new development using the pillars is basically we are trying to keep the front side illumination technology, meaning we want to keep the low cost of this technology, and taking the benefit of 3D, of the BSI, and combine them into this solution, because this would be a game changer if it's successful, because we're targeting here two major things: quality of the image and the resolution. Okay, again, before we conclude this in this minute, basically the intelligence is only present in the world, in the biology, in the physical world. All what we need to do is to extract that and implement it. The same way that intelligence was extracted by mankind by looking at the math evolution, it started by abstracting the concept from nature and then put them in paper. The same thing we are trying to do, and we are suggesting to come back to biology and learn from it the intelligence and implement it into engineering. Currently, I'm doing that at the CMOS imaging, but later on I'm moving to the Internet of Things, which really needs some intelligence to have business in life. And the last thing is that we really need to get to the fundamental science, means the biology and the physics, basically, in order to advance the microelectronic systems, or the rich people. We need the money from these guys to come back to these guys to make the education more interesting and the business more fruitful. Okay, and these are some of reference that I have used, and thank you very much for your attention, and welcome for all your questions.
Okay, thank you very much, Dr. Faisal. So let's ask maybe one or two questions. Do you have any questions about the seminar, what we just heard on imaging sensors? So let me ask you this question.
Sure,
you know, especially in terms of the analogy with the biology, you mentioned these fish that can actually expand, you know, the depth, basically.
The photocells, yes.
The height, yeah?
Yes.
And the analogy was that, you know, there's the height of a photocell that can actually be doing something similar. But how do you make that height adaptive?
Very good question. Actually, I heard about that question again.
Yeah.
So the idea in terms of implementation, there are many techniques actually. But to adapt the length to go up and down, that's not the purpose of it. When we try to apply that into engineering, we either go with the highest efficiency available, meaning that, okay, we have to find the optimal length and then design and then move on. That's when we talk about PV, because we are looking for highest efficiency possible, okay? So we do that and then bingo. Now the adaptability that you are mentioning is actually for vision, for imaging.
Yeah.
And for that, you don't have to adapt, okay? You can easily implement in every single pixel, especially that the footprint in here is quite small. You can have one pillar for low light vision and one pillar for low light vision. So you don't have to adapt, okay? So you can, because the footprint is so small that you can have two transducers in there, one transducer for bright light, one for low light, and multiplex between them, and your life will be fine. This is the easiest solution. Down the road, oh yeah, there are many tons of ideas about that. You can basically have some sort of heating system, okay, that can basically be around this photodiode and heat it, pass the current, heat it a bit. But again, this is an idea that we can try, and that's why we are doing research. But in the simplest way of doing this is basically just, because the footprint of the pillar is so small, you can have 2 or 3 if you want. One for the highest sensitivity for very low light, and one for regular light. And this has to come with technology, computer-aided design tools to estimate that, and then you move on. And then you multiplex between the two at the system level, and basically you can have information when it's bright light, when it's low light, just by playing between these two diodes. Want to take this diode or this diode, up to you, and based on the applications.
So yeah, go ahead.
Yeah, about the same feature, the height of these, the receptors.
Photodiodes, actually. Photodiodes, yes.
Photodiodes, yeah. So I would think they would impose a constraint on the density of your pixels also, right? Because they impose some shadows on each other, or
actually, that's
the light.
That's a very good question, and it's not about the shadow actually about that. The nice thing about this picture, and this is one of the intelligence aspect of the biological vision, is that this rod is actually fully depleted, meaning that the photon that will have an impact on this photodiode is the photon that comes directly vertical. The one that comes oblique will see a very small depletion region, and basically will go through without even being sensed. So the photons that come directly, vertically to the photodiode has the highest chances to be, to have the quantum efficiency or the probability to create electron hole pairs and being converted to an electrical signal. But the shadow is absolutely out of the question. They will not see their adjacent pixels. All what they see is actually the vertical light.
I thought the reason you wanted to increase the length is to increase the surface area to have more light integrated.
No. The surface area is not our business. Okay. For that surface area, maybe in the charging business, but for imaging, I want to enhance the conversion. And by enhancing the conversion, or what we call the sensitivity, we do that by taking the smallest footprint, which is the basis of the photodiode, okay, and basically being able to see the light only through the length of the photodiode instead of the plannar. Okay. So now I'm sensing this way instead of this way. Okay. On this dimension instead of these 2 dimensions. And it's not about increasing the area. That's for capacitors and all these things, but not for imaging. No.
Okay, any other questions for Dr. Please, questions.
I still don't understand why not to optimize, like Dr. Ibrahim asked, why not to optimize the pillar array spacings and the height? I think spacings are also important and it needs to be considered, because there will be diffraction effects and some other effects that requires electromagnetic simulations to study, right?
That's right.
I don't know if you consider this, but right now I'm focusing on the height. Why not to optimize the height for whatever intensity it is, and then use it for all the time?
That's exactly what we are doing. That's exactly what we're doing. But Dr. Ibrahim, what he mentioned is basically how you can implement the adaptability, how you can change this H or the height of the pillar on the fly. You cannot do that with silicon because the material is there. How are you going to elongate it? It's not elastic. That's the thing.
I think the origin of the question was because you mentioned about
No, I'm not biomimicking the elongation. I'm mimicking the fact that the photosensor is not planar. I'm biomimicking that it's a 3D structure rather than planar.
Okay.
That's what I'm biomimicking.
Okay,
I'm not biomimicking the dynamics of the
you are using
photocell.
this as a justification for why you
Exactly. That's exactly my point. What I said is that we have proven that semi-empirically. The biology did that in real life. We could do that. That's why I call it biological proof. So the biology proved that the sensitivity is actually proportional to the height.
Right.
So what we need to do now is just basically make it and sell it. That's the point. But we are not biomimicking the elongation aspect, means being elastic, elongate. No, that's not in our business now.
Okay.
Question?
Go ahead.
I also have a comment. I don't believe that sensitivity is directly proportional with age. Because when you do the optimizations or electromagnetic simulations for such pillars, you will see that there will be an optimum height where you will optimize absorption by minimizing deflection and then so
Absolutely, you are absolutely right. And that's exactly what I'm doing right now. Is basically this condition, it's not verified or it's not true for any height. No, there's an optimum height or there's a range of height where it's true. But outside that range, boom, it's off, because otherwise I can make it long as much as I want.
Yeah, exactly.
That's crazy. But this, what I want to say, that there's a truth, there's an interval of truthness for this we can use, and outside that, it's out of business. So we are trying to look at that window and move on, okay? But it's not true outside that window. Outside that window means all these parameters that you mentioned, and also we are not counting the leakage currents and all these things which are coming to eat us as well. As you increase, the surface increase, the leakage counts will kill your signal, boom, 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 boom. So it's not true for any height, but it's definitely true for a certain range of height, for certain conditions. And those conditions, we need to meet the market, and we meet also the industry. Because what you see in simulation is not always verifiable or doable in the foundry. So the foundry will tell you, no, we can do this, we cannot do that.
Yeah, they
So exactly, it's not a simple thing. What we are talking here is that there is a window of opportunity, and let's look at that, and that's why we are doing research and getting our salaries, I guess.
Okay, great. Thank you very much for the
Thank you for your questions.
Yeah, so let's thank the speaker again. Thank you very much.
Thank you very much.
We can see you back here.
Thank you.
And hopefully, we'll be in touch. So I think Suela, right?
Yes.
Yeah, she's doing optics. So
Okay,
and she's also doing PV.
I have some business cards if you want to.
And we have a lot of people who are also in the IC business,
That's great.
who are doing actually interfaces for sensors and so on and so forth. So
Okay,
we have
that's
a
great.
really good group of people.
Yeah, I'm definitely interested to meet people here.
Thank you
Thank you
so
very
much.
much. Thank you. Thank you very much. Appreciate it. Thank you.
Thank you very
Thanks,
much.
Dr. Brahim. I really
Yeah,
appreciate
No
it.
problem. Thank you very
Thank
much.
you so
for,
much.
coming over.
I hope that it was.